To get an accurate read on the velocity of the metal ball and the plastic ball moving through this tube, I'm going to need at least 5 sets of displacements and times. Okay? Now you can use the same displacements for both the metal ball and the plastic ball, but you also don't have to, depending on how they fall. Okay? So first things first, I just need to have some tape marks on here so I can tell where I'm making my displacement measurement. So let's put a piece of tape here. Okay. And I'll put another one here. Now it doesn't actually matter where exactly you put your tape marks, as long as you can measure how far it is from one to the other, and as long as you can time how long it takes for the plastic or the metal ball to move from one to the other. So if I take my meter stick here and I measure how far it is from one tape mark to the other, let's see, that is about, I'm gonna say it's close enough to 50 centimeters. So from one tape mark to the other, if I see the metal ball fall from one point to the other, it's gonna move about 50 centimeters. Now displacement is a vector, and that's how velocity gets its vector status, by coming from displacement, which means the direction matters. To show the direction in my measurement, positive and negative are gonna describe up and down. So the displacement of the bubble moving through this tube would be positive, whereas the stuff falling through, like the plastic and the metal, are going to have a negative displacement. Okay, so when I flip this over, I'm going to time out how long it takes for the metal ball to go from tape mark to tape mark to go 50 centimeters. And since it's going downwards, I'm going to make that a displacement of negative 50 centimeters. Okay, I'm going to do the same thing with the plastic ball, where I've got to time out how long it takes, but I have to be careful about which way I'm sending them. If they're on top of each other, like they were just there, the metal ball is going to try and push the plastic ball to go faster, and the plastic ball is going to slow down the metal ball. So we're not going to get a good accurate reading of either of them in that case. We need to make sure they're falling independently of each other. So now if I switch them back to the other side, the metal, boom, boom, goes there, and the plastic goes there. I probably can't time them both out at the same time. It's too quick. So I'll just do them one at a time. So I'm going to pull up a stopwatch on my laptop. Okay. I've got to flip them back the other way so they're not stuck to each other, so they fall independently. All right. Here, I'll do this. I'll hold my mouse like this so I can start and stop the timer. All right. I'll flip them over. I'm going to just focus on the metal ball first. Start, stop. Okay. I've got that time. I'm going to use the same tape marks for the plastic ball, just so I don't have to keep moving the tape every single time I do this. Again, I got to flip it back over, because right now they're going to travel with each other. Okay. Now this time I'm going to watch the plastic ball instead. Start. Stop. Okay. Once I have a displacement and a time, I can make a data point on a graph. I'm going to collect all my data points first before I make my graph, so that way I've got all the information I need. Okay? I can also calculate, using each displacement and time, what the speed should be in Google Sheets, as long as I can, set up the equation to do so. In the past, the equation's already been set up, so this time I'm going to show you how you can make your own equation in Google Sheets. Once I've got my displacement and time for a set of tape marks, I can scooch these tape marks somewhere else. I can get them closer to each other or farther apart. So like maybe I want to do one that is 10 centimeters apart, or I want to do one that's like 75 centimeters apart. Okay, doesn't really matter, again, where you exactly put those tape marks, as long as you can measure what the displacement is between them. Keep in mind that it's going to be a negative value because your balls are going to be moving downwards through the tube. Positive is upwards, negative is downwards. And as long as you can time it out, then we should have some pretty good data. Now keep in mind that since these liquids are going to have different thicknesses, some of these are going to allow your metal and plastic ball to move faster. Like this one moves pretty quick, and some of them are going to move slower. Make sure that you make your tape marks work for you. If you have a really fast moving one like this, okay, then the metal ball is really going to be hard to measure accurately in a small displacement. Like if I put my tape mark like here and here, because when I flip this over, okay, I missed it. Like, not only is it going to be hard to start the stopwatch when the metal ball hits it, but also it's going to be hard to stop it real quick by the time it passes by there. I'm not going to get a good accurate measurement. Now, if you have a liquid that's moving really slowly, like, let's see, this one I think moves pretty slowly. Okay, like if you watch the plastic ball here, that takes quite a while. This is not the slowest, thickest liquid, so this isn't actually all that bad, but there are some that move very, very slowly. If you put your tape marks way far apart from each other and you're waiting for the ball to move from the top to the bottom, it's going to take a long time. So for the sake of efficiency, if you're working with something that has a very thick liquid and the metal and plastic ball are moving very slowly, put your tape marks close together. As long as we've got 5 different sets of tape marks, it doesn't exactly matter how close or far they are. We just need 5 different data points of them moving some displacement and the time it takes to get there. With that, we can make the graph and make a trend line that eliminates the errors as best as we can. And the slope of that is going to be the velocity, the speed with a direction, the vector version. Since our displacement is going to show that our metal and plastic ball are moving down through the tube and not up, okay, our graph is going to kind of look upside down, where we're going to start from a high point and work lower as time goes on. Okay? And your displacement values on your y-axis are all going to be negative. So we'll be kind of starting up here at 0, and as something travels farther and farther downwards, we'll have larger and larger negative numbers as time continues to go on this way. So it's going to look kind of weird. However, because the slope is still the rise over the run, the displacement over the time, whether or not it's going up or down doesn't make a difference. We can still compare the slope as how fast or slow the metal or plastic ball is going. So this is an example of what my lines might look like, where this kind of lighter magenta line would be something like my metal ball, and the purple line here would be something like my plastic ball, where the metal ball is going to move quicker, so it's going to cover a greater displacement in some amount of time, whereas my plastic ball is going to take longer to make the same kind of displacement. Or if I run them for the same amount of time, then the metal ball should make it a farther distance. So my graph is going to show that the slope of the metal ball is going to be steeper than the one of the plastic ball. Even though it's moving downwards, we can still tell it's steep, just going the other direction. And we can still get a value the same way, just the slope will be a negative number. The velocity will be a negative number to show that it's going downwards instead of upwards.